Hey everyone, and welcome. You know, in machine learning, it's so easy to get obsessed with one thing, getting the prediction right. But what if I told you the real magic isn't just in the prediction itself, but in knowing how confident the model is about that prediction? That's exactly what we're going to unpack today as we dive into the world of uncertainty. So let's just chew on this for a second. A model tells you there's a 90% chance of success. Sounds amazing, right? You're ready to go. But what if that model has only seen like a handful of examples before making that call? Suddenly, that 90% feels a little shaky, doesn't it? Its own confidence in that number could be through the floor. And that distinction right there is the absolute heart of what we're talking about today. All right, here's our game plan. First, we'll get on the same page with a language of probability. Then, we'll look at a classic method for finding that one best answer. From there, we'll explore two really cool but totally different ways to figure out how much we should actually trust that answer. And finally, we'll wrap it all up. Okay, first things first. If we're going to talk seriously about uncertainty, we need to be speaking the same language. And that language, my friends, is probability. It's the whole toolkit we use to put a number on what we don't know. So it turns out, uncertainty isn't just one big blob of confusion. There are actually two distinct flavors. On one hand, you have aleatoric uncertainty. Think of this as the universe's built in randomness, the classic coin flip, right? Even if you know for a fact a coin is perfectly fair, you still have no idea what the next flip will be. They can't get rid of that. But then there's epistemic uncertainty. This is about our ignorance. It's the uncertainty we have because we just don't have enough information. Like, is the coin really fair? If you've only flipped it twice, you can't be sure. The key difference? We can fight this kind of uncertainty with more data. All right, so how do we actually start modeling things? Well, a really common place to begin is with this powerful idea called maximum likelihood estimation, or just MLE. And the goal is actually super intuitive. Find the one single explanation for the data that makes the most sense. Let's make this real. We're just going to flip a coin. We toss it 10 times, and we get this sequence you see here, 3 heads and 7 tails. Now, our model for this coin is going to be incredibly simple. It's just one number, a parameter we'll call W, and it stands for the probability of that coin landing on heads. So here's the core idea of MLE. We're going to try out every possible value for W. What if the coin is super biased towards tails? What if it's perfectly fair? For every single possibility, we ask one simple question. How likely would it have been to see our actual data, 3 heads and 7 tails, if this was the true nature of the coin? The value of W that makes our data seem the most plausible, that's our minor. And this little equation here is how we do it. It's called the likelihood function. It looks a bit formal, but all it's saying is this. Take your guess for W, the probability of heads, and raise it to the power of 3, because we got 3 heads. Then take the probability of tails, which is just 1 minus W, and raise that to the power of 7. That's it. This gives us a score for any W we want to test. So, if you imagine plotting that score for every possible value of W, you get a curve. We're just looking for the very peak of that hill. And for our data, that peak happens right when W equals 0.3, which, makes sense, right? 3 heads out of 10 flips, 3 divided by 10 is 0.3. That's our single best guess. Okay, so we're done, right? The answer? 0.3. Well, not so fast. Think about it. We only flipped the coin 10 times. How much should we really bet on that 0.3 being absolute truth? This single number feels brittle. It doesn't tell us anything about the range of other plausible values. And this exact problem leads us to a huge fork in the road in statistical thinking. On one side, you have the frequentists. They'd say, look, that coin has one true, fixed probability of landing heads. We don't know it, but our job is to estimate it. Then, on the other side, you have the Bayesians. They have a totally different take. They say probability isn't about the coin, it's about our belief about the coin. We can be uncertain about that parameter, and we can use probability to describe our beliefs. It's a really deep difference. So let's walk down the frequentist path first. Their solution to this uncertainty problem is super clever. They basically ask a what-if question. Okay, I got 0.3 from this specific set of 10 flips, but what if I had collected a different set of 10 flips? This whole idea is called the bootstrap. Here's how it works. You start with your original 10 flips. Then, you create a new pretend dataset by randomly picking 10 flips from your original set, and the key is with replacement. So you might pick the first heads 3 times and one of the tails not at all. For that new sample, you calculate the best guess for W. Maybe it's 0.2, maybe 0.4. You write it down. Then you do it again and again, thousands of times. What you end up with isn't one number, but a whole pile of estimates. And the spread of that pile, how wide or narrow it is, that is your measure of uncertainty. Okay, let's back up and go down the other path now, the Bayesian approach. These guys don't mess around with creating fake data sets. Instead, they tackle uncertainty head-on, using probability distributions to represent what they believe about the parameter W. The engine that drives this whole thing is the famous Bayes' theorem. Now, don't let the math scare you. The concept is beautiful. It just says your new belief, the posterior, is a sensible mix of your old belief, the prior, and the evidence you just saw, the likelihood. You start with what you think, you look at new data, and you update your opinion. It's common sense, just formalized with math. So this idea of a prior belief is key. How do you tell a computer what you believe? You use a probability distribution. For a coin, we could start with a distribution that's peaked right at 0.5. This is us literally telling the model, hey, my starting assumption before we see any data is that this coin is probably fair. And this table shows that update in action. You start with your prior belief that the coin is fair. Then in comes the data, the likelihood, which is suggesting a bias towards tails. And the posterior is the result, our new updated belief. The math is simple. We just add the heads and tails to our prior parameters. We started off thinking the coin was fair, but our belief has been pulled towards the evidence. We've literally learned. So, okay, we've seen these two totally different ways of thinking, the bootstrap and the Bayesian method, to get past just a single number. So what's the real takeaway here? Well, the most important thing is that even though they come from different philosophical universes, they're both trying to solve the same problem, quantifying our epistemic uncertainty. They both agree that a single number like 0.3 is just not the whole story. The frequentist way simulates what could have happened with other data. The Bayesian way explicitly models our evolving belief. Both give us what we really want, not just a prediction, but a measure of our confidence in it. And honestly, this is the whole point. Probabilistic machine learning represents a huge shift in mindset. It's about building models that don't just give answers, but also know what they don't know. It's about getting our models to say, I'm really confident about this one. Or, more importantly, you know what? On this one, I'm pretty much just guessing. So I'll just leave you with this final thought. As AI gets baked into more and more critical parts of our world, medicine, finance, self-driving cars, which do you think is actually more dangerous? An AI that makes a wrong prediction, or an AI that makes a wrong prediction but delivers it with absolute unshakable false certainty? Understanding uncertainty isn't just some academic exercise. It's fundamental to building AI we can actually trust.